On this page of notes, we're going to review solving systems of equations in two variables, particularly choosing the best method. Substitution will be our best method if one of our variables has a coefficient of 1. We can see that that's not the case on this first example, so on this one we're going to use elimination. Elimination means that we choose a variable to eliminate, and it doesn't matter which variable we choose, but we need to eliminate that equation from that variable from each equation. So when I look at this equation, I'm going to choose to eliminate the y's. No reason why I chose y over x in this particular case, I just did. So in order to eliminate the y, I'm going to take this entire equation and multiply it by a -7. And I'm going to take the entire second equation and multiply it by 2. All that matters when I'm choosing my variable to eliminate is that once I'm done multiplying the two equations, that the variable I've chosen to eliminate, that their coefficients are the same but opposite signs. When I take my first equation and I'll multiply it by a -7, if I uncover, I can see that I distributed that -7 and I had -49x. I distributed the -7, got a -14y, and a -105. When I distribute the 2 to the second equation, I can see that my resulting equation looks like this. Now I can simply add the two equations together, so the elimination method is often referred to as the addition method. When I add my two equations together, I can see that the y's will drop out, and I get -43x equals -55. Continuing my solving process, I get kind of a gross looking answer for x, and that's perfectly fine, especially when we're solving systems of two equations. Since this is a review of an Algebra 1 concept, don't assume that your answers have to always look like nice numbers. Once I solve for one variable, I can plug it back into either one of my original equations. It does not matter which one. I take the x and I either substitute it into x on the first equation or in the second. So when I substitute that in, I've chosen the first equation, so I have 7 times my strange looking answer for x plus 2y equals 15. I don't want to convert these to decimals. Instead, I want to keep in mind that I want to work with my fractions. So I'm going to take my 7 times my 55 over 33. I'm going to multiply those together and then move them to the other side. Once I move them to the other side, I get my common denominators, just multiplying the 15 by 43 over 43. And then I get 2y equals 260 over 43. You can see in the red here, I've multiplied each side by 1/2 so that I can get rid of this 2 on the left-hand side. Multiplying these fractions together, I get my final answer of 130 over 43. It's also important that we remember to write our final answer as an ordered pair x, y. So make sure that as you're working, you're clearly keeping track of what answer is x and what answer is y. Continuing on to my next example. This problem, you can see I've taken one of my equations and solved for a single variable. That means that this problem is more easily going to be solved by substitution. When I look at my coefficients on each of my variables, I can see in the first equation that the y has a coefficient of 1. So I simply solve that equation for y so that I can do a simple substitution, taking the -5x plus 16 and substituting it into the second equation. Be very careful with your parentheses when you do your substitution, because the 10 from the second equation will have to distribute to the entire expression that we determined for y. I distribute that 10. From there, I can just continue solving this problem as if it were just an Algebra 1 problem, collecting my x's and moving my 160 to the other side. In this case, you can see I chose to move my variables to the right-hand side to keep my variables positive. Again, I get a very strange value for x, which is perfectly fine. Now I'm going to take that equation, or that answer for x, and substitute it again into either one of my original equations, or more easily substituting it into the rearranged equation. So when I take my 163 and I substitute it into here, I get my -5 times my 163 over 46 plus my 16. And again, you can see here in red is where I chose to work with my fractions, getting the common denominators. My final answer for y. And then, of course, I have to pull them together and write them as an ordered pair. My last example, I have several things going on this problem. First of all, I can see that this problem is more easily going to be solved by substitution, simply because the y in the first equation has a coefficient of 1. In the second equation, what I notice is that I have all these fractions. Remember, the easiest way to work with our fractions is to simply eliminate them by multiplying through by the least common denominator. So I'm going to multiply this entire equation by a 6, resulting in this new equation, which is clearly much easier to work with. So now I've solved for y, I've cleared my fractions, and now I can do my simple substitution. I'm simply taking my -2x plus 5, substituting it in for y, remembering my parentheses. I distribute and solve. Keeping track of all of my signs and collecting my like terms, I get an answer of x of 9/8. Again, when I go back to substitute, it doesn't matter whether I substitute in here, 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 or here to solve for the remaining variable. The easiest, of course, would be the y. I substitute in again. I find my common denominators. In this case, when these two multiplied, when my -2 times my 9/8 multiplied, it reduced to a -9/4, which would make my common denominator something a little bit smaller. Adding my fractions after my common denominators, I get 11/4, and my final answer written as an ordered pair.